Alrighty, lads and ladies, welcome back. Today we are going to introduce something pretty different from what we've been talking about, but a little bit related to parametric curves. We're going to learn how to work in a new coordinate system, which you may have seen in your trigonometry class if you had a thorough trigonometry class. Hopefully you have, but I know not everybody has. So I'm going to try my best to recap the stuff you're supposed to learn in trig before we move forwards. And the new coordinate system that we're talking about is called polar coordinates. So the goal for today is to get you comfortable thinking and working in polar coordinates. This, of course, is MAC2312, section number 004, which means this is a Calc 2 class. And the date is the 15th of April, 2022. This pen might be dying. So today, well, this one too, really. Today we're going to be talking about polar coordinates, and this is section 10.3. We may or may not get through the whole section today because we are going to spend some time just sort of reviewing what polar coordinates are and how to think in them. This section moves pretty quickly. So it introduces polar coordinates. We talk about how to go back and forth from the standard XY coordinate system to the R theta, which is the polar coordinate system. We learn how to graph functions in the polar coordinate system. And then also in this section, 10.3, we learn how to find tangent lines to polar graphs. Now, in theory, I'm supposed to assume that you guys all know what polar coordinates are. You all know how to go back and forth from Cartesian to polar. You all know how to graph curves in the polar coordinate system. And if that was genuinely the case, then we could get through all of this today, no problem. However, I think those things are probably uniformly not true. So we're going to build from the ground up the polar coordinate system today. And that means we'll get to do a little bit of graphing, but the bulk of the graphing work and definitely the tangent line work we'll have to save for Monday of next week. So let's get started. The normal XY plane, as you know it, is sometimes called the Cartesian plane. And that's named after the man René Descartes, who was a philosopher in the Renaissance era. You've heard the saying, I think, therefore I am, or cognito ergo sum in Latin. That saying, I think, therefore I am, is from the same guy, René Descartes. He was a philosopher, mathematician, true Renaissance man. He was the first one to study what we call now analytic geometry. You may have noticed the title of this class is Calculus with Analytic Geometry. Well, every time you draw a graph in the XY plane, you're doing analytic geometry. Analytic geometry just means like you're doing geometry, but you have a coordinate system associated, which allows you to do some analysis of that geometry rather than doing everything purely in geometric terms. Normally, if I want to specify the location of a point in the plane, I give you an x value and a y value. Right? The x value would be here, and the y value would be here. And to get to this point, you would say, okay, I'm going to go over x and then up y. That is not the only way to tell you where this point is. Right? There are actually many other ways to tell you where this point is. The normal way of going out x and then up y, that is the Cartesian or rectangular coordinate system. The polar system says to do something a little bit different. It says from your point, imagine a ray emanating from the origin. This has a length, which we can call r, usually thought of as a radius. And that also creates an angle down here we call theta, the polar angle and the polar radius. When you do this, you sort of induce a little right triangle. The idea here is that instead of telling you x and y, I tell you r and theta. So if I tell you, okay, start facing out along the positive x-axis, rotate up by theta, and then walk out r, that will also get you to this point. So we think of this point as being xy in the Cartesian coordinate system. We think of it as being r comma theta in the polar coordinate system. So these are the Cartesian coordinates, and these are the polar coordinates. It's the same thing as telling you x and y. I'm just giving you directions. How do you get from the origin to this point in the plane? And everything that you can do with xy coordinates, like draw graphs of functions, calculus, areas, tangents, all that stuff, you can do in the polar system as well. The polar system has a bunch of advantages over the Cartesian system. It also has some disadvantages. It is especially nice when you're dealing with a situation that is radially symmetric or has a lot of rotational symmetry for reasons we'll see in a little bit. The first thing we need to do, though, is talk about how to go back and forth. If I give you the Cartesian points, like I tell you, this is the point, 3, 2, how do you find r and theta? Conversely, if I give you the polar coordinates, r and theta, can you tell me the normal Cartesian coordinates, x and y? And the trick to going back and forth is this little right triangle. The big idea, going back and forth, is that this side length here is x, right? Because you go over by x. And this side length here is y, because you go up y. And then you can use some sort of basic trigonometry. You know that if you look at the cosine of theta from this right triangle, that should be the adjacent over the hypotenuse, right? The adjacent over the hypotenuse, which is x over r. And if you solve this for x, you get x equals r times the cosine of theta. And we can do the same thing with the sine of theta. Sine theta is the opposite over the hypotenuse. So sine theta here would be y over r. And I can solve this for y, getting y equals r times the sine of theta. Other relations that we can deduce from this triangle, because it is a right triangle, it satisfies the Pythagorean theorem, x squared plus y squared equals r squared. And one more relation we can get involving the angle theta is that the tangent of theta would be the opposite over the adjacent. The tangent of theta must be equal to y over x. And you should think of these four things as being like a little dictionary to go back and forth from one language to the other. So if you want to take a point that's given to you in Cartesian coordinates and write it in polar coordinates, you would use generally the bottom two equations. If you want to take a point that's given to you in polar coordinates and put it in Cartesian coordinates, you would use the top two equations. But we need to hold on to all four of these. All four of these are very, very important. the first thing I'd like to do is just get a little bit of practice plotting some points in polar coordinates, and then we're going to practice going back and forth from polar to Cartesian, vice versa. Let's plot the polar points. How about 2, pi? We could do 2, pi over 4. We could do 1, negative pi over 2. We could do s as maybe something like how about 3, 5 pi over 6. We could do this by converting each of those polar points into their Cartesian form and then just plotting the Cartesian points, right? Find x and y. But I want to think purely in terms of the polar coordinate system here to get you comfortable before we start transcribing back and forth. Make sure that we're good with the way polar coordinates should work in your head. So here's how you do it. I'm going to mark this as 1, 2, 3 along the right facing horizontal axis. Generally, by the way, we call the thing that you normally think of as the positive x-axis. In this setting, we call the polar axis. And the point of the origin we call the pole. Oh, damn, these pens are dead. It's a brand new one. Motherfucker. MAC. Call the origin generally the pole. And we call the thing you normally think is the positive x-axis, we call it the polar axis. So to find the point P, which is 2, pi, that means r is 2 and theta is pi. What we do is we walk out along the polar axis until we get to 2 here. And then I'm going to rotate around by pi. So let me put some other tick marks here to kind of help us out. So I'm going to walk out 2 along my polar axis. I'm going to start here, and then I'm going to rotate around by pi radians. And that's going to put me right here. So that's the polar point 2, pi. That's the point P. To get to the point Q, which is 2, pi over 4, again, I walk out 1, 2 along my polar axis, and then I rotate up by pi over 4. So this is the point Q. If I want to plot the point 1 comma negative pi over 2, I walk out 1 along my polar axis, and then I rotate pi over 2 in the negative direction. So this would be the point R. And then finally, if I want to get to the point S, I walk out 1, 2, 3 along my polar axis. And then I need to rotate around by 5 pi over 6. That's like right here. This is the polar point S. And you may have noticed something here. It's convenient to think of the polar system as a bunch of concentric circles, where you walk out to the correct circle and then rotate around on that circle some amount. There are, in fact, things like polar graph paper. All right, you see this? Where you've got all of your concentric circles and some of your angles labeled. Oh my God. Just look at the motherfucking thing. More bullshit. What I want to see. There we go, right? So here's like your polar coordinate system. Instead of a grid, like the XY plane, when you look at regular graph paper, you think of that as a grid of horizontal and vertical lines. Well, your polar grid is a bunch of concentric circles, right? Which tell you sort of what your radius is. And then all of these rays, which tell you what your angle is. So if I wanted to get to the point like 4 comma pi over 6, I would go out 1, 2, 3, 4 along my polar axis. And then I would go up along that circle to pi over 6. So here's the polar point 4 comma pi over 6. If I wanted to get to the point, say, 6 comma negative pi over 4, I would walk out 1, 2, 3, 4, 5, 6. And then I would walk down in the negative direction by pi over 4, which is going to be back here. I guess right here. This would be 6 comma negative pi over 4. So this is how we plot points in polar coordinates. There is some subtlety. R is not necessarily always going to be a positive number, and we're going to learn how to deal with that. But this is the basics, right? This is where we need to start. Questions about how we were able to plot these points, P, Q, R, and S in the polar coordinate system? Okay. The next thing I want to talk about is converting from Cartesian to polar and polar to Cartesian. It's easier to go from polar to Cartesian. So the first thing I'm going to do is find the Cartesian coordinates of all these points. For example, let's find the Cartesian coordinates for the points P, Q, R, and S from the previous example. The trick to all of this is to remember x is r cos theta and y is r sine theta. That's all we need. Because if you know r and theta, then you can plug those two things in here to get x. If you know r and theta, you can plug those two things in here to get y. So the first point P had polar coordinates 2, pi. So r is 2 and theta is pi. And this one, I bet you could tell me what the Cartesian coordinates are just from looking at the picture where we already drew this, right? What's the x value here at this point P? Almost. Yeah, -2, right? The x value is over here to the left, so it's -2. And the y value here? Yeah, it should be 0. All right, let's see if this shit works. I sure hope it does. Therefore, x should be 2 times the cosine of pi. Well, that's 2 times -1, which is -2. Thank God. All right, because the cosine of pi is -1. And y? That should be r sine theta. That's 2 times the sine of pi. The sine of pi is 0, so that's 2 times 0, which is 0. So P in Cartesian coordinates is -2, 0. In Cartesian coordinates. Okay, let's do the others. This is our answer for the first part, -2, 0. The point Q had polar coordinates 2, pi over 4. This is polar. So r here is 2, and theta here was pi over 4. This one's a little harder to guess, right? If you look at the point Q in our drawing above, it's not immediately obvious what the x value is or what the y value is. So here we really do need to use the trig. This means that x should be 2 times the cosine of pi over 4. And the cosine of pi over 4 is √2/2. So this is 2 times the square root of 2 over 2, which is just the square root of 2. Y should be r sine theta. That's 2 times the sine of pi over 4. Well, the sine of pi over 4 is also √2/2. So the y value here is also the square root of 2. So Q in Cartesian coordinates is the point square root of 2, square root of 2. And if you look at the picture, that makes sense. I'll give you a second here to make sure you've got this written down. All right, if you look at the picture, square root of 2, remember, is about 1.4. So yeah, like 1.4, 1.4-ish. That makes sense. Okay. r in polar coordinates was 1, negative pi over 2. Those were the polar coordinates. So x here should be 1 times the cosine of negative pi over 2. What is the cosine of negative pi over 2? Very good, that's 0. Y should be 1 times the sine of negative pi over 2. What is the sine of negative pi over 2? Very good, that's negative 1. So r in Cartesian coordinates is the point 0, negative 1. And if you look at our picture, that matches up, right? Here's our picture. R is the point whose regular xy coordinates would be 0, negative 1. All right. And then our last point there, S, had polar coordinates 3, 5 pi over 6. So here r is 3 and theta is 5 pi over 6. That means x should be 3 times the cosine of 5 pi over 6. The cosine of 5 pi over 6 is negative square root of 3 over 2. So this is 3 times negative square root of 3 over 2, which is negative 3 root 3 over 2. And y, that's r sine theta, that should be 3 times the sine of 5 pi over 6. The sine of 5 pi over 6 is positive 1/2. So that's 3 times 1/2, or just positive 3/2. So the point S in Cartesian coordinates is negative 3 root 3 over 2, 3 over 2 in Cartesian. So this is not hard, right? Going from polar to Cartesian coordinates, you just plug into those formulas, those trig formulas I gave you. X equals r cos theta, y equals r sine theta. Nothing fancy. I want to talk about going back the other way, going from Cartesian into polar. And it might seem like it's just the same thing in reverse, but it's actually different. So you do need to be a little bit careful here. And in order to show you why you need to be careful and exactly what you need to be careful about, we need to take a brief diversion into this possibility that the radius r can be negative. So I want to talk about polar points r, theta, where r is negative. There's sort of two ways to think about this. I'm going to show you the easier conceptual way first, and then I'm going to show you something that relies on symmetry, which will be more useful when we start talking about graphing polar functions. So let me begin by just saying we can plot polar points like -3, What do we want to do? How about -3 comma 2 pi over 3 by walking out along the, call it the negative polar axis, then rotating. Okay, so normally if I was going to go to 3 comma 2 pi over 3, I would walk out 1, 2, 3, and then rotate up by 2 pi over 3. But here I've got -3 comma, rotate up by 2 pi over 3. Here I've got -3 comma 2 pi over 3. So here's -1, -2, -3 along my polar axis. So I'm going to walk out to -3 and then rotate in the positive direction by 2 pi over 3. Which is going to put me right here. So this is the polar point r comma theta, where r is -3 and theta is 2 pi over 3. Let me go ahead and plot the point +3 comma 2 pi over 3. So if I walk out 1, 2, 3, and then I rotate up by 2 pi over 3, that's going to put me right here. Here's the point r comma theta, which is 3 comma 2 pi over 3. And I ask you, do you see any symmetry here? If I was already at this point and you wanted to tell me how to get from this point to this point, what's the most convenient way to describe the relationship between these 2 points? I'm doing it right now. It's true that, yeah, the r values are 3 and -3. But think about what action you could do to this thing to turn it into this thing. Like drag left, right, flip over vertically. What sort of action could I perform on this point that will flip it into this point? We reflect through the origin. That's the symmetry. To get from 3, 2 pi over 3 to -3, 2 pi over 3, we take this point and we reflect it through the origin. And there's nothing special about the point 3 comma 2 pi over 3. In general, r comma theta and -r comma theta can be swapped meaning you can go from one to the other by reflecting through the origin. And this is a big deal. You might say, why? Why not just use positive values for R all the time? Many answers to that. The first of which, and most important, is that we're going to study functions like R equals f of theta. And sometimes those functions are going to spit out negative numbers. So you got to know how to deal with the R value being negative. Another point has to do with what's called the non-uniqueness of polar coordinates. And this is a bit of a bummer. So I want to take a second, make sure we all have this down, make sure we're comfortable with the picture and the symmetry there. Okay. So, note. Polar coordinates for a given point are not unique. There's a separate thing. It's going to connect back to what we're talking about, meaning by this I mean for any point P, there are many sets of polar coordinates for P. This is in stark contrast to Cartesian coordinates. Cartesian coordinates are unique, right? If you point to a point in the XY plane, you point to a point, there is one X and one Y for that point. There's only one way to tell you how to get to that point using Cartesian coordinates. There are many ways to tell you how to get to that point using polar coordinates. Not just two, not just three, there's infinitely many. And the reason for that is twofold. First, the trig functions are periodic with period 2 pi. So for any particular point, r comma theta, just add 2 pi to theta, or add any multiple of 2 pi to theta, and you'll get back to that same point. The other sense in which these are non-unique comes from the symmetry we just described between r and negative r. So here's an illustration. Let me plot the polar points. I'll call them P1 is 2 comma 3 pi over 4. P2 is 2 comma 2 comma negative 5 pi over 4. And P3, let's call it negative 2 comma negative pi over 4. And Q1, let's call this 1 comma negative pi over 3. Q2, oh, damn it. Q2, we can call 1 comma 7 pi over 3. Or sorry, not 7 pi over 3, damn it. 5 pi over 3. And for Q3, let's do negative 1 comma, and then two pi over 3. All right, I think I chose these correctly. I got to think about this just a little bit. It's not the most obvious thing in the world. But let's plot all 6 of these polar points. Let's see what we get. Okay, I'll call this 1, and I'll call this 2 along my polar axis. I want to get to 2 comma 3 pi over 4. So I start by walking out 1, 2, and then I need to rotate around 3 pi over 4. Where's 3 pi over 4? Well, this is 1 pi over 4, 2 pi over 4, 3 pi over 4. So there it is. There's the polar point P1. What about P2? 2 comma negative 5 pi over 4. Okay, so I walk out 1, 2, and then I need to rotate around backwards by 5 pi over 4. So there's negative pi over 4, negative 2 pi over 4, negative pi over 2, negative 3 pi over 4, negative 4 pi over 4, negative pi, negative 5 pi over 4. Oh shit. It's the same point. You see, whether I walk around positive 3 pi over 4 or walk around negative 5 pi over 4, I get to the same point. What about P3? Well, P3 says walk out negative 2 and then rotate not the forwards direction by pi over 4, but rotate in the backwards direction by pi over 4. Oh shit. P1, P2, and P3 are all the same point. Different coordinates though, right? Totally different numbers in here. These guys both have positive 2 for R, but different thetas. This one has a negative R and a different theta. I could have kept going like this. I could give you infinitely many polar coordinates that get you to this same point here. Let's try the Q points. So we're going to go to 1 comma negative pi over 3. That means I walk out 1 and I rotate backwards by pi over 3. So that's going to put me like right here. This is the point Q1. Q2, I'm going to come out to 1, right? Walk out 1 and then rotate around by 5 pi over 3. Well, okay, here's 1 pi over 3. 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Uh-oh. Q1 and Q2 are the same point. What about Q3? Well, Q3 says start over here at -1, go left here, -1 along the polar axis, and then rotate by 1 pi over 3, 2 pi over 3. Yep. Same point. So polar coordinates are not unique. Cartesian coordinates are unique, and that's a very nice thing. In mathematics, we love it when things have unique representations. So let me talk a little bit about what's going on here. In general, the points P equals R theta are the same as R comma theta plus 2n pi, or 2 pi times n, where n is any integer, positive or negative. So once you have your theta value, you can either add or subtract 2 pi, and you'll get another one, right? So if you subtract 2 pi from 3 pi over 4, you get -5 pi over 4. That's where I got this. And P equals R comma theta will be the same as -R comma theta plus an odd multiple of pi. Again, where n is any integer. So there's infinitely many ways to represent any point in polar coordinates. All right, we could keep going. We could keep coming up with other polar coordinates that take you to this same point. They come in two families. They come in the 2 pi kind of family here, where you get to your point and then just rotate around again, or rotate around again. They also come in this other family where you go to your corresponding point with a negative radius and then walk around by pi, or walk around by 3 pi, or walk around by -pi. Another little fact here. If we require that R is positive and theta comes from the interval 0 to 2 pi, then polar representations are unique. But generally, we can't do this. We can't always require those things. Right? Sometimes we have to deal with R being negative. Sometimes we have to deal with theta being negative or bigger than 2 pi. There's just nothing we can do about it. Okay. I suppose this should be greater than or equal to 0. Okay. So this is the polar coordinate system. It's not terribly hard to get used to, but you do need to practice. When WebAssign tells you to graph or plot a polar point, do yourself a favor. Do not just, oh, this has degrees, we want to work with radians. Oh, 17, that's a weird choice. Does this one have a pi over 2? It doesn't. Do yourself a favor and actually plot the things. You can download some polar graph paper like this, which can be very useful and actually use it to draw, or you can just draw on your own paper. But when WebAssign tells you to plot some points, don't just click the graph until you get it right. It's the same sort of bullshit I'm always talking about. When WebAssign tells you to graph something, graph it by hand. Then pick the graph in WebAssign that matches what you draw. Do not just go through the homework clicking until you get it right, guessing. That will not teach you the shit. So now that we've talked about the non-uniqueness issues, we need to practice going from Cartesian to polar. And since there are multiple polar representations for each point, I'm going to ask you to come up with 3 of them. You'll have problems like this in your homework. You'll have problems like this on your exam. I can go back for just a second, sure. Do you want the top here or the bottom? Oh. Here we go. Okay, moving on. Like I said, we've gone from polar to Cartesian, right? I give you r and theta, you tell me x and y. Now that we know about non-uniqueness, I can ask you to go from Cartesian to polar. And more specifically, I can ask you to give me several polar representations that satisfy certain conditions. So I'm going to say find 3 polar representations three ordered pairs r comma theta for each Cartesian point given at least one having r less than 0. At least one having r less than 0. So let me specify a few Cartesian points. Let's start with some relatively simple stuff like 0, 2. For q, I could use negative root 2, negative root 2. And for r, let's use the square root of 3, negative 1. All right, so for each of these, I'm going to give 3 sets of polar coordinates. It is a good idea to begin by plotting these. This will give us a general sense of what's going on, and it will also help us check and see if our answers make sense. So So I'll mark off here, how about 1 and 2. 1 and 2, something like that. -1 and 2, something like this. The point P is at 0, 2 in Cartesian coordinates, so P is right here. The point Q is at -√2, -√2. Now √2 is about 1.4, so -√2 is like right here. -√2, -√2 is like right here. Here's the point Q. Square root of 3 is about 1.5. It's a little bigger. So like here is +√3, -1. Here's the point R. And I want to find for each of these 3 sets of polar coordinates. The point P we probably could do without thinking too hard at all. But let me kind of warm us up, because for each of these, what we're going to do is we're going to use those equations. So P is 0, 2. That's your X and your Y. And we have the equations. Maybe I'll put them over here. X squared plus Y squared equals R squared. And tangent of theta is equal to Y over X. I'm going to use these guys. Oh, first page. So for this guy, I know that X squared plus Y squared is R squared. That means that 0 squared plus 2 squared equal to R squared, which means 4 is equal to R squared. So R would be plus or minus 2, right? When you take the square root on both sides, you get the plus and the minus. We also know that the tangent of theta should be equal to Y over X. Well, here that means that tangent of theta is equal to 2 over 0. And that's a bit of a problem, right? Dividing by 0 there, that's strange. But we know that tangent is sometimes undefined. What is the angle here for the point P? What are some theta values I could use? Good, pi over 2, right? Tangent is undefined at pi over 2. Where else is tangent undefined? Yeah. So I could add or subtract pi to this number. So 3 pi over 2, or negative pi over 2, or negative 3 pi over 2. All of these are angles where tangent of theta is undefined. So the radius r is either going to be +2 or -2. And the angle theta is going to be any angle that would appear on this list. But you can't just take anything from this list and anything from this list. You have to pair them up appropriately, right? Like p is not the same as 2, 3 pi over 2. If I walk out 2 and go around 3 pi over 2, I'm going to land down here, which is not where I want to be. So some polar coordinates for p are, let's start with the natural one, where r is positive and theta comes from the interval 0 to 2 pi. If we impose that restriction that we talked about, then what are the coordinates for p? Where r is positive and theta is between 0 and 2 pi. Yeah, very good. If I walk out 2 and I rotate up by pi over 2, that is sort of the most natural way to describe this guy. If I walk out by 2, rotate up pi over 2, and then rotate another 2 pi, what's that going to give me? That would be 2 comma pi over 2 plus 2 pi. 2 pi is the same as 4 pi over 2, so this would be 2 comma 5 pi over 2. Another one which would work, if I go out to -2 and then rotate backwards by pi over 2. So -2 comma negative pi over 2 would work. And we could keep going. -2 comma +3 pi over 2 would also work. But I'll stop here. All right, there's many, many ways. Questions on what we did with the point P here? All right, we're going to move to Q. Same sort of shit. X squared plus y squared equals r squared will get us r. So I plug in the x and the y. That's negative square root of 2 squared plus negative square root of 2 squared equals r squared, which is the same as, if you square negative root 2, you just get 2. So this is 2 plus 2 equals r squared. So again, here, yeah, 4 equals r squared. I just realized I think all of these had radius 2. So r has to be 1 of plus or minus 2, just like the last guy. So it says, so some polar coordinates for P are, yeah, some polar chords. So I'm abbreviating the word coordinate as chords. Some polar coordinates for P are, and then these 3 points that we gave. Let's keep working on the point Q. So we know that R has to be one of plus or minus 2. Tangent theta should be equal to y over x. So tangent theta is negative root 2 over negative root 2. In other words here, tangent of theta is 1. And this will give me a bunch of theta values. Tangent is equal to 1 when theta is pi over 4, 5 pi over 4, negative, let's see, what else? So pi over 4, 5 pi over 4. We could also think of this as negative 3 pi over 4. Or negative, let's see, 1, 2, 4, 5, negative 5 pi over 4. I'll just stick with these. These are good enough for now. Negative 1, 2, 1, 2, 3 pi over 4. Yeah, fine. So here are 3 theta values we could use. All right, we're just trying to find all the theta values that satisfy tangent theta equals 1. And I'll put the answer up here. So some polar coordinates for the point Q are, well, let's see. Let me zoom out a little bit, we can see the picture. If I want R to be positive and theta to come from the interval 0 to 2 pi, I fit this. Yeah. Then I would walk out 1, 2, and rotate around by 5 pi over 4. So I could say 2 comma 5 pi over 4. And that's that nice one where R is positive and theta is from the interval 0 to 2 pi, but there are many others. I could use negative 2, go out negative 1, negative 2, and then rotate down by pi over 4, rotate backwards pi over 4. So that would be negative 2 comma negative pi over 4. Oh no, sorry, that's the positive direction. Yeah, I'm sorry. That's the positive direction of rotation counterclockwise. So we got negative 2 and then rotate in the positive direction by pi over 4. And if I want one using the negative 3 pi over 4, I could say I'm going to go out 1, 2 and rotate backwards by 1 pi over 4, 2 pi over 4, 3 pi over 4. So positive 2 comma negative 3 pi over 4 all get us to that same place. So this is our final answer for the second part. So our final answer for the first part. All right. Maybe I won't go ahead and do R here. Maybe I'll leave R as an exercise because I do want to get to a little bit of graphing today. Any questions on where we're getting either of these lists of polar coordinates from? So I'm going to leave the last part there to you as an exercise. Go ahead and try to find 3 polar representations of the point R, which was or somewhere. Yeah, √3, -1. You've got problems like this in your homework. You don't have to do that if you don't want to. I want to talk now about graphing functions in polar coordinates. And the examples we're going to look at right now are very simple. But we will look at more complicated examples starting on Monday of next week. And then we're going to start doing calculus with polar coordinates. If you want to graph a function and you don't know anything other than how to plot points, the only thing to do is to make a table and plot points. And I'm going to start with some very simple examples, like I said. When you're learning how to graph curves in regular XY space, like back in middle school, you would make a table, right? And so here, that's what we're going to do. We're going to sketch. Oh, and the types of functions you begin with, right, are the simplest ones imaginable, constant functions. Sketch the graph of the constant function. Let's do R equals 3. So I think of theta as the independent variable and R as the dependent variable. And I just have to pick some theta values to plug into my function now. Theta equals 0 is a good one. We should let theta go from 0 to 2 pi. Maybe I'll do pi over 4 and pi over 2. And then maybe I'll skip to pi. And then maybe I'll skip to 3 pi over 2 and then to 2 pi. Now, the fact that this is a constant function means no matter what theta is, R is always going to be 3. So when theta is 0, R is 3. When theta is pi over 4, R is 3. When theta is pi over 2, R is 3. When theta is pi, R is 3. And so on. Right? This is what a constant function does. No matter what input you give it, it spits out the same output. So if I want to draw this graph, we go 1, 2, 3 along my polar axis. 1, 2, 3. 1, 2, 3. All right. When theta is 0, R is 3. So there's theta equals 0, R equals 3. It's the polar point 3, 0. The R comes first, remember. When theta is pi over 4, R is 3. So I walk out 1, 2, 3, and then I rotate up by pi over 4. I'll put me like right here. Here's the polar point 3, pi over 4. When theta is pi over 2, R is 3. So I walk out 1, 2, 3, rotate up by pi over 2. Here it is. The polar point 3, pi over 2. And then I skipped to pi. So when theta is pi, R is 3. So I go 1, 2, 3, and then rotate around by pi. Here's the polar point 3, pi. We skip to 3 pi over 2 next. The polar point 3, 3 pi over 2 is here, and then 2 pi. What do you think this curve is? Yeah, if r is always 3, then no matter what angle theta is, you're always going to be on this circle of radius 3. So that's the curve. So r equals a constant, right? There's nothing special about 3 here. R equals c, where c is a constant, is always a circle of radius, I should say absolute value of c, because if you took r equals -3, it would be the same thing. Centered at the origin. So just like how in your regular XY life, y equals a constant is always a horizontal line, in your polar life, r equals a constant is always a circle centered at the origin. The other one worth looking at here is theta equals a constant. That's the other super simple one. Let's do that. So let's sketch a graph of the constant function. Let's do theta equals pi over 3. Same deal, we make a table, theta and r. So if r is 0, then theta is pi over 3. If r is 1, then theta is pi over 3. If r is 2, then theta is pi over 3. If r is -2, theta is pi over 3. If r is -1, theta is pi over 3. Theta is always pi over 3. We're looking at all the points in the plane where theta is equal to pi over 3. If I start plotting these points, we'll see another simple pattern develop. I'll mark off like 1 and 2 along my polar axis here. So the polar point is 0, pi over 3. That means I don't walk out at all. My radius is 0. That means I must be at the origin. This is the point 0, pi over 3. If I look at the polar point 1, pi over 3, I'm going to walk out 1 and rotate up by pi over 3. That's going to put me somewhere right around here. It's the polar point 1, pi over 3. If I look for the polar point 2, pi over 3, means I go out 1, 2, and then rotate up by pi over 3. It's going to put me right about here. It's the polar point 2, pi over 3. And then if I want -2, pi over 3, I would reflect this point through the origin. If I want -1, pi over 3, I would reflect this point through the origin. This is -1, pi over 3. This is -2, pi over 3. And you see the pattern here, right? This is a line. This is a line through the origin, making angle pi over 3 with the polar axis. And that angle here is always pi over 3. And in general, the polar graph theta equals c is always a line through the origin making angle c with the polar axis. So these are your two simplest possible examples, right? Constant functions. Now, of course, just like when you're studying regular functions, constant functions are kind of boring. And we want to look at much more exotic stuff. So I'll give you two more examples here today. The last one is going to be kind of what we'll be doing most of next week. I'm just trying to warm you up for it. Any questions about how we got these two graphs or the two notes there? Okay. Two more little examples, and I'll let you go. Let's sketch the polar function r equals theta. No longer a constant function. Okay. Still, we're going to make a table. Usually, theta will be the independent variable, so we'll pick some theta values and see what r values we get out. If theta is 0, r is 0. If theta is pi over 4, r is pi over 4. If theta is pi over 2, r is pi over 2. If theta is pi, r is pi. You see where this is going. If theta is 3 pi over 2, r is 3 pi over 2. If theta is 2 pi, then r is 2 pi. I'll stop here. And let's say theta runs from 0 to 2 pi. Generally, when we graph polar curves, we will use this as our domain. That's usually the domain we're going to use. This is actually a curve you've seen before. And by the way, if you haven't noticed, I did post a bunch of stuff to Canvas for you guys the other day. I know I don't want to go too far over time here. But I just want to point out that there are a bunch of new things under both the parametric curves section here. I put all this stuff in here for you guys, lots of videos, lots of Desmos graphs. One of those Desmos graphs for the parametric curves is the same as the graph we're going to see here. And then there's a bunch of stuff here. These animations for polar plots, these are really good. But for you guys, based on what we're doing today, I would start with the top few videos here if you're looking for extra stuff. I'll come in here and try to draw this curve. I'm going to give myself lots of space. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. Okay. When theta is 0, r is 0. So I'm starting at the origin. When theta is pi over 4, how big is pi over 4? Let's see. Oh, shit. That's so stupid, isn't it? Let's get a feel for the size of these numbers. Pi over 4 is about 0.78. So when theta is pi over 4, r is pi over 4. It's just a little smaller than 1. We'll put that like right here. When theta is pi over 2, r is pi over 2. It's about 1.5. Okay, so I'll walk out to 1.5 and I'll rotate up by pi over 2. Here's the polar point. Pi over 2, comma, pi over 2. When theta is pi, that's a little bigger than 3. R should also be pi. So I'm going to walk out here to pi and then rotate around by pi. It'll put me about here. This is the polar point. Pi, comma, pi. When theta is 3 pi over 2, that's about 4.7. So I'll walk out r to about 4.7 and then rotate around by 3 pi over 2. It'll put me about here. This is the polar point. 3 pi over 2, comma, 3 pi over 2. And when theta is 2 pi, r is 2 pi. That's going to be a little bigger than 6. So here's the polar point, 2 pi, comma, 2 pi. So if you connect these, you get this spiral shape. And it would keep going and growing and growing, and so on. The stuff from 0 to 2 pi is just this first stuff, right? This is an Archimedean spiral. Okay. I did want to show you one more, but that one more requires a sort of different technique. So maybe this is a good place to stop. We'll stop here for today. And then on Monday of next week, I'm going to show you more sophisticated techniques for graphing polar curves, better than just plotting points. Plotting points is kind of middle school stuff. We want better skills, better tools, and we will have them. The general trick is going to be to graph the thing first in rectangular coordinates and then transfer that graph into polar coordinates. But this stuff takes some time to get used to, so it's okay. We're going to finish this up on Monday of next week, when we will also talk about tangents in polar coordinates, right? How to find derivatives. And then we will, on Wednesday of next week, talk about how to find areas and arc length in polar coordinates, both of which are kind of interesting, especially areas. But this is where I'm going to leave it for now. Please work hard on that homework set. I'll take a look, and if there's anything in there that we haven't talked about yet, I think there is, then I'll extend that a little bit further if needed. So don't panic, but do as much of the homework as you can. And I will see you guys on Monday. Oh, your study guide is out, by the way. I published the study guide last class. So yep, that's it for me. Any burning questions before I end the meeting? Okay, then, oh, I see something here. For example, we're getting a reference sheet. No. No cheat sheets. We gotta know this stuff. Yeah. So the power series that you're responsible for knowing are those in the table in section 1110. Right, and we really do have to know these. So a nice table here. The ones that you need to know, all of them except for the last one, right? So this last guy, don't worry about him, but all of the rest, you gotta know them by heart. And it's not too much, and these are such fundamental things that you really do need to have them on the top of your head, but no cheat sheets. Any other questions? Alrighty then, I'm gonna end it here. I'll see you guys on Monday.